All right, I'm going to make a quick recording or a quick class, hopefully, an example to demonstrate the mass moment of inertia, not mass moment of inertia, area moment of inertia. All right, so it's really easy to get that confused between area moment of inertia and mass moment of inertia for a couple of reasons. One of the main reasons is that most of the time people use capital I as the symbol for both mass moment of inertia and area moment of inertia. It's actually going to be second area moment of inertia is actually the technical name of it. So what you could do to try to differentiate it, remember that mass moment of inertia was used in dynamics, and it's a resistance to turning, really, is what that is. It's like the equivalent of mass for rotation, okay? But for mechanics of materials and for stress, we use area moment of inertia, which really is a measure of the distribution of the area and helps us. We use it in the beam bending stress of MC over I. That I that we have, that's going to be for area moment of inertia. Okay, so I'm going to continue recording here, and I'm going to switch over to OneNote. Okay, because it's easier to write. I want to minimize this thing over to the right. Yeah, I guess that's good enough. All right, so we're in OneNote here. So let me just write that down real quick. Okay, so the difference here is mass moment of inertia. Mass, and I'll just write capital M, little o, big I. The mass moment of inertia is going to be, would be used in the sum of the moments is equal to I alpha, right? So that's the mass moment of inertia. So that gets used in dynamics. Whereas the area moment of inertia, MOI, gets used in stress is equal to M, which is the moment times C divided by the moment of inertia. So this is where we're going to use this, and that's in mechanics of materials. Okay, so just be on the lookout that yes, it is easy to get them confused, but in this class, we're not going to use this mass moment of inertia thing. Okay, they're very common though. They have a lot in common because the way that they're formulated, at least for integral, if we're going to take the integral to find them, is to take the distance that we have of something squared to the small portion of mass, but in our case we use area instead of mass. So they're very, very similar. Most of the time we talk about moment of inertias. We're going to be specific, and we're going to use I, and those are going to be about a particular axis, right? As that's in the same plane. Now we also can do a polar moment of inertia, and that's about the axis that's coming out of the page, right? And they too are related to each other. Now these are the integral forms of these. And we're usually not going to we just want to know that that's where it comes from. We're not necessarily going to do that. We're not going to do that in this class. We're going to show that we just take standard shapes and we add them together. And the way that we add them together is to use our good friend PAT, the parallel axis theorem, which states that if you want to find the new moment of inertia, take the moment of inertia about the centroid of the piece and then add to it the area times the distance that you're moving, right? So it's important that you get the correct distance because so like for instance, if I wanted to make the mass moment of inertia of this object right here about this x-axis right here, I would need to take it from its centroidal axis and move it down this amount right here. In this case, that's dy. right? But originally I found it about its centroid, which is this guy right here. So I would say that this I that I want about x is going to be equal to I about x prime. See, this is the x prime right there. And most of the time, there's a couple different ways we write this, but most frequently we put a bar over the I to signify that that's the moment of inertia about the centroidal axis. And then we add the area times the distance that we're moving squared. And that gets it about this piece right here. So if we were like trying to bend it about this axis right here, right, about that x prime, this is the moment of inertia we were trying to do. If we had to move it bend it about this axis instead, we would need to do it about this ix right here. An interesting thing I should point out for circular pieces where we do this polar moment of inertia, that we could actually end up finding what the polar moment of inertia is by adding together the moment of inertia about the one axis and the moment of inertia about another axis. An interesting way to put the thing. So this is where it's located in Shigley in table A18 back in the appendix. It kind of gives you this rundown of what you're looking at. And it gives you the basic shape. So these are the ones that you really care about. That we're going to use, because the method we're going to use to find moment of inertia is almost always going to be by composites, and that's going to be taking simple forms and adding them or subtracting sometimes them together and moving them with the but in order to add and subtract them, they need to be moved from their own centroidal axis to the overall the axis that we care about. Okay, so let's just break it down. But also, before I go further, I want to mention that these are good things to memorize if you haven't already. BH cubed over 12, right? And I just memorize that and say, okay, well, the base is whatever is parallel to the axis I care about, and H is the one that's perpendicular to the one I care about. So you don't really need to know two different forms of the thing, just with whatever axis that we're looking at. This should actually even have a bar over them to be to highlight that these are centroidal moment of inertias. And then a good one to also memorize is that the moment of inertia I about for a circle is d fourthed pi over 64, pi over 64 times d fourthed. Also, for the polar one is actually those two plus each other. So instead of so when it's about the central axis, when it's spinning, and that's going to be used for torsional stress. Remember, that's going to be tau is equal to TR over J. If we want the J of it, that's the polar moment of inertia. We could see that they are 1/2 of, or excuse me, I guess it would be twice what the twice what the regular moment of inertia is. Wow, can't talk. I'm tired. All right. Also know that if you had a cylindrical one, you could just subtract them from each other, the large one from the small one. So we have those same equations, just a big area and then subtracting out a smaller area. So here's the example I chose to put in here. And the best way to do these composites is to make a table. Most of the time, you're going to end up having to make two tables. It's hard to squeeze them all into one table just because it gets very long. So I'll methodically pick this apart. I've already written this out, so I will just kind of move along. I decided to make these into parts. Make the designation here. We didn't necessarily have to. We could have also chosen like this and like that. But for this one, we're going to choose right here and right here. Now, your homework problem is only 2 parts, but I made this one harder. So I'm going to designate these parts as 1, 2, and 3. The first step of any of this is to find the centroid. So that's actually the first table. And so what I'm going to do is I'm going to make a table on the segment. So 1, 2, and 3, I've numbered the segments. We're going to find what the area is all right, for that particular segment. We're going to find the distance of the centroid to and this can be an arbitrary axis. Okay, when we do the moment of inertia part of it right there, that has to be it matters what axes that we're talking about, but in this case we're going to go an arbitrary one, and that's going to be about the x right here and about the y. All right, so we're going to call the distance, I think, xi and yi. That means the i's mean each segment, what they are designated. And then, so this is really going to be, maybe I'll write area here. I'll go ai. And then I went xi bar ai, and then y bar I, ai. All right, so here's my table right in here. And I think I'm going to cheat some as I went through here. I'm looking at the solution to what I've made. I think I took a couple shortcuts. And I didn't really make my table big enough for what I wanted to do. Wish I had redrawn it, but I'm going to make it fit. Okay, so from this first area of segment 1 right here, we're going to say that that's going to be 1.3 times 1, and we know that the area is 1.300. Okay, area of segment 2 is going to be 0.5 times 3.8. Okay, so if you look at this thing, we had to pick the thing. Okay, I've written down 3.8, so it's right already there. And then it ends up being 1.900 if you calculate the thing out. We're going to do segment 3. That's going to be 3.6 times my thickness, which is that shown? I guess I forgot to write it in there. It's 0.5. Forgot to write it in. So 0.5, and so we easily see that that's 1.800. All right, so now we're going to pick from the center of each of these pieces to the arbitrary axis. So the xi, the distance, is going to be, okay, so the first one's going to be hard to do. That's great. So we're going to get this distance from right here. That's going to be 0.5 plus 3.8 plus, and it looks like 0.5 because it's half of 1. So that should be 1 plus 4. Okay, no, excuse me, that's the y direction, right? So this is the distance from the x-axis, that y bar. So that's going to be 4.8. That's the one I just calculated. For xi, that's going to be the distance from the y-axis, that xi, and that's going to be right to here. Or in other words, it's going to be half of 1.3, or 0.650. Writing very small. Okay, to build this guy up a little. Come on, zoom, please. Okay, thank you. For part 2 here, from the x, okay, that's only a 0.25, right? Because that's right in the center, right there. Yep. And then for the x position right here for 3 is just going to be 1.8, so half of 3.6. Similarly, the y distance to the center of we already did part 1. For part 2 is 2.4. Let's see, why is that? Because it's going to be half of 3.8, and then plus 0.5, so 2.4. Okay, and then once again, the distance in the y direction is going to be 0.25. Now we multiply this one, xi, so the xi times the area, we do that 0.845. Multiply this 4.8 times the 1.3, and we get 6.24. Do the same thing here, and we get 0.475. Then again, 4.56. I really should get 4 sig figs as I'm doing this, so I made the mistake when I originally wrote the thing out, so don't be like me. Do what I say, not what I do. Okay, so the xi, ai, this is 3.24. Once again, 4 sig figs would have been better, and probably will have some error. And that right there, that's only 2 sig figs. That's really bad. I was a very bad person when I made this before, so I need to reform. If we add all these up in this column right here, so we say what we're really doing is we're taking the sum of this right here. If we add that up, we end up with 4.560. And by the way, these units, that would be inches cubed. If you're paying attention, inches cubed, right? Because it's area, which is inches squared, times distance, which is another inch, so it's inches cubed. And then for this column right here, y bar, AI, that ends up being 11.250. And of course, this really lends itself to an Excel spreadsheet, right? But I do want you to do it by hand so that I can see that you've done it. It's a good exercise. All right, last thing that we do to get the centroid now is to take. Oh, by the way, I never got this total area right here, so we should really take the sum of all those parts, and we sum them up, and we find that it's 5.00 inches squared. So now, if we want to get the centroids, we could say that x bar overall of the thing is equal to the sum of, and I guess I wrote it this way, so I'll write it again this way: xi bar ai divided by summation of ai, right? So 4.560 divided by 5.00, really 000, we end up with 0.912 inches. And here for y bar, similarly, we just take 11.250 divided by 5.000, and then we end up with 2.25 inches. And then, as with any problem that we need to do, we should just give it a sanity check. It's always good to get a sanity check. So this guy on X means it's going to, that we've decided that the centroid in X direction is about maybe not quite like right here, maybe kind of like somewhere along that line. And then along the Y direction is 2.25. Okay, so this is probably going to be somewhere along here, right? So where those two match up, this is kind of where the centroid is. So I like to do the little centroid symbol right here and put that right there. It looks like it's not a very good centroid symbol. Let me draw it again. I'll draw the centroid symbol. Looks like this. It looks like on a crash test dummy, you'll see these little pieces right here, so the camera to focus in on. But I like to use that as the centroid thing. All right, so we found the centroid. That's our first thing, task to do. I'm just going to go ahead and let me wipe out the rest of this right here. Let's see if I can get rid of this. What do I do? Just delete? Well, let me delete. Yeah, there you go. Okay, so because I want to use the figure again, maybe I should undo that. I'll undo that and see, undo. And if I can grab that, can I grab it? No. Let me see. Can I? Let me go back to this other piece. Great video. Yeah. All right. Let me go over to this guy. Go down. Let me grab him again. All right, so I'm going to copy. Where you go? Copy. Where the hell are you? There, copy. All right, so get back down here. Come on. There you go. Yay. All right. So I'll paste him in here and see if it'll let me paste. Oh, nice. Look how small he is. Itty bitty. Oh, you can't get him on there. How come I can't drag him up? Drag. Oh, boy. All right, you gonna make him big? You're not gonna let me do it, are you? Come on. Oh, you jerk. All right, whatever. Okay, so, fun with What a whole lot of fun we're having here. All right, so I'm just gonna like delete all this nonsense here. All right, I'll do it like I said I was gonna do. And because I'm so lazy, I'm not going to edit any of that out. So you get to watch me making a fool of myself. Okay, so we're going to do this. Now we're going to make another table, right? From what we had previously, X bar was 0.912 inches and Y bar was equal to 2.25 inches. That's what we got. So like right up here somewhere was our centroid. Now we make another table. And we're going to go by segment, and I guess I gotta need it'll be much wider, and I'll write let's go segment, and then I'll go I about X I, right? So that's going to be the individual one. Then I'll go A. I guess I go no. This is A overall. Okay, so A overall, and then I guess I'll just say dy squared. And then I'll write AX. I'll go prime, right? So I'm going to call this X prime right here. I'll call this Y prime. That's the new axes. That's centered at the centroid. And then for another part of my column here, I'll write I, Y, I, and then A dx squared, and then I'll have I y prime. Okay, so hopefully I'll have enough room here. 1, 2, and 3. So what I want to do is I want to find the moment of inertia of each segment about its individual centroid. So for part 1, that's going to be 1/12, right? So it's BH cubed over 12. So the base for this one is 1.3 because we're doing it about the X, right? So that's the base. And the height of the thing is going to be 1 inch high cubed. We end up getting 0.1083. Right, and so, okay, so for piece 2, 1/12 right here, and now its base is going to be 0.5, and its height is going to be 3.8 cubed, 2.286, right, and now for the last one, 1/12, and take 3.6 is the base, right? So here's 3.6 is the wide part for that in that axis, and then 0.5 is the height cubed. So it's 0.03750. Okay, and I'm going to run out of room here for sure. So, how am I going to do this and not make a big mess? I guess I will erase this part right here, and I'll just go ahead and only do about the x-axis, and then I'll do the y-axis another thing. So like I'd say in class, don't kill yourself by trying to squeeze everything in one space. So here's a good demonstration of what not to do, is trying to squeeze everything into a little narrow space. So okay, so I take the area times the distance the thing moves. So what I'm really doing here is I've written across the top. I've really written the parallel axis there. I've really written x like this right here. I'm saying the new moment of inertia about the new axis, which is the centroidal axis, is equal to the one about each moment of inertia, each part, plus a times the distance that they're going to get it moved. So that's really what I've done. I've just separated out and flipped it around for the thing. All right, so the area of segment 1 we knew was 1.300. The distance that it's going to move, its original location was up here, right? But now it has to move down to there. So that distance that it's going to be moved is really going to be like 4.8. If you remember from our previous thing, we said, hey, that was the position with respect to the x-axis. It was 4.8 upwards. So we're going to take it from 4.8, but we're going to move it down. So we're going to have to, this distance was like 4.8 right up to there. So we subtract out where the centroid was going to be, or the centroid distance, which was the 2.25. But that whole thing squared. And I guess I didn't add up what that thing was, but I ended up adding whatever this was to whatever what I got here, and I end up with 8.562. Then I take my area of the segment 2, which is 1.9, and 2.4 was the distance from the base at X to its centroid. And then, of course, I subtract out 2.25 and square it. And if I calculate those up and I add it to the segment moment of inertia, it's 2.329. And then I do it once again for segment 3, 1.8 times the 0.25, right, minus my 2.25. Now, this is going to end up with a minus number, but we square it, so it doesn't matter like what order we subtracted the things from. And if we calculate all that out, add it together with the I bar, we end up with 7.238. And then we can add all of those up right here at the base, and now we have I X of the whole thing, actually. You know, these were individual parts, right? But we moved all the parts, so we assembled them together. So the total piece right here ends up being 18.13 inches. And the units of these are inches fourthed, okay? Now, we could do all that same thing, but this time we're going to do it for about the y-axis as well. Right, so about the y-axis, I would do all the same. I don't know if I need to do this again for you, but I might as well. All right, so we're here. All right, so just for convenience sake, I'm going to go ahead and erase all of this and write the thing out so you can compare it later. Hopefully you have the idea at this point. This wasn't my best effort here. But let's get rid of that X. And that's not going to be, all right, so now it's going to be dx is the good thing is moved, but this is yi, and this is going to be y prime. So filling the thing out, we go, now it's at 1/12. Right, but the base now of the above is going to be 1, right? Because we're doing it about now it's going to be about this axis right here. It's the individual centroid of segment 1. So its base is 1, and its height is 1.3 cubed, and so that ends up with. Did I even write it out? I think I did. It's coincidentally, it's like almost a like a dyslexic version of the other answer. Interesting. All right. So 1/12, and once again, that's going to be 3.8 is now the base, right? So it's this distance is the base times the height, which is 0.5 cubed. What does that end up being? That's 0.03958. For very thin things, when the thin thing is aligned down by the long axis of the thin thing, you'll see that it has a very small moment of inertia, which makes kind of sense. There's no much resistance to bending for something that's thin when you're bending it along the thin axis. All right, so 1/12 here. Okay, so that's 0.5 is the base for this, and 3.6 cubed is the height, and that ends up being 1.944, so a lot more than that other the thin piece that we had at segment 2. Now we get the area, and we say that's 1.3 for segment 1, and 0.65 is the distance from the y-axis to its centroid, and we subtract out what we got for the centroid distance of 0.912, and we square that, right? So now we can add up that whole thing, and it comes out to 0.2723. And then moving along, area 1.9, 0.25 minus 0.912 squared, and that ends up being 0.8722, and then 1.8 times, and now we go 1.8, it's just a coincidence that they're both 1.8, minus 0.912 squared, and we get 3.363. We add all those up. Now we're going to get IY of the whole thing now about its centroid is 4.51 inches fourthed. All right. So it apparently is has a much larger moment of inertia. We got both previously the X moment of inertia about the X centroidal axis was 18.13. So it's significantly more about the x-axis than it is about the y-axis. So that's the end of my spiel here. Hopefully that'll help you. That's a refresher, give you the tools to get back and do the homework problem. Thank you.